Good morning, everybody. My name is Thomas Humbert. I'm working at Toulon. I'm a research engineer, and I will talk to you today about the MAINE Flow duct facility. So these are some works we have done in collaboration with Yves Aurégan at Toulon and with people from the CTTM in Le Mans. So the MAINE Flow actually means multimodal acoustic impedance eduction. It's a big duct facility, so you can see just the in black center the duct measurement duct, which is 14 meters long, and the rest is a wind tunnel within Sillon, the fan, and basically the rest is more or less silencers. So the duct measurement duct section is 15 per 28 centimeters. We can reach flow velocities up to 240 meters per second. We have nearly 190 acoustic sources on each side of a test section, which is 80 centimeters long. And we have 120 microphones. So you can see two pictures of the acoustic sources and the microphones and the test section where we can mount some acoustic liners. So one of the goals of this facility is to qualify aeroacoustic liners for high acoustic levels, so high SPL, typically 150 dB, fast grazing flow up to Mach 0.6, and multiple incident angles, so high order modal acoustic content. I show you here some liner examples from simple single degree of freedom liners and more modern complex research liner we are doing at the lab. And also some aircraft nacelles, because if we are interested in measuring with ISPL and fast grazing flow, it's because the liner that you can see close to the fan in the nacelles will endure this kind of environment when in flight. There are also plenty of research paths we will follow with this facility, as you can measure it by the number of lines on that slide, from grazing flow effects to high order modes, propagation and absorption, development of experimental techniques, because it's never easy to measure in those conditions, and also provide data for validating numerical tools that are developed at the lab. So it's not the first time we are talking about this duct facility in conference. So I won't talk today about how we choose source position, microphone number, and positions. There are some publications about that, and I will just focus today on modal control, modal decomposition, and transmission loss measurements. So why modal decomposition is a big deal? Usually in the small ducts we are used to, typically in the lab 4 per 5 centimeter rectangular cross section, only plane waves propagate in the range of frequency we are looking at. And so we only need 2 microphones on each side of the sample, for example, to characterize the scattering matrix. In practice, we use 3 or 4 on each side, but 2 would be sufficient. But when your rectangular test section is much larger, like the 15 per 28 centimeter here, even at 600 Hertz, you will have a first high-order mode that will be propagative. And if you consider 4000 Hertz, there are 24 modes that can propagate. So at least you will need 48 microphones. Actually, we have 60 on each side. But in all cases, it's never simple to find the amplitude of each mode in both directions when the modal content can be so complicated. The problem can be described by the following equation, with P being the pressure at each microphone position, for example. And on the other side, you have the propagative waves amplitude, so amplitude per each mode and each direction of propagation. And interesting component will be the propagation matrix, which is known, as well as the pressure at each position. And this matrix will be just a function of the size of the rectangular cross section, so W and H, the positions, and an actual propagation term that will depend on the position X and the wave number of the mode of the waves. But we can calculate this wave number if we know the frequency, the Mach number, temperature. So actually the only unknown is the modal amplitude. But since you see this simple matrix formulation, these amplitudes can be found using pseudo-inversion of the matrix M. One way to validate that we are doing this thing good is to cut the duct and to put a plate just after, for example, the microphone upstream test section. So I will show you some results performed on reflection coefficient of this plate, which should be 1 for certain modes. And this result, so here, have been computed using 70 different excitation, acoustic excitation. So I plot the absolute value of the reflection coefficient as a function of frequency. And so considering the 4 first modes, so the plane waves is 0, first higher order mode is 1, 2, 3. And when you have lots of propagating mode, actually, so you can, this is now a matrix of reflection coefficient. And what you see is actually what could be expected, being the reflection coefficient, the diagonal is 1, and the other terms are 0. So actually, this validates how we decompose the acoustic field in order to catch the wave amplitude and then to compute the reflection coefficient. So this will be useful for the rest of the study, but not for this slide. Now we want to control the acoustic incident field because it can provide some interesting features of the liners. The first way to do that is we can call it the direct method or the beam forming method. So the goal is to incite one desired mode to propagate. And we will do that by sending the same acoustic amplitude at each frequency to all of the sources, for example, to the upstream sources, but we'll just use phase difference so that the right actual wave number that corresponds to the design mode is favored. Here I'll show you the result in terms of amplitude of the upstream modes. If I attend to help more the plane wave than the others, it's on the top left corner. And so I see that with the blue curve, actually I managed to get 145 dB at each frequency, and with an emergence that go from 10 dB at low frequency and so to something more complicated after 2500 Hertz. It is working a bit better for higher order modes. But yeah, there are some improvement to do for high frequencies. And actually it's working with the same performances when there is flow, Mach number 0.2. So all these measurements were performed without liner. So just we removed the reflection plate and just the hard wall duct. As we were not completely satisfied with what's happening at high frequency, we decided to use another method that consists in 2 steps. The first one being to link source channel commands to the measured pressure. So in practice, we just send as many sweep independent signals as there are some sources in order to link each source channel command to the measured pressure in the duct close to the test section. And then we know with the pseudo inversion of the matrix, propagation matrix, how to link this pressure to the modal amplitude. So actually we know with that how to link the source channel commands to the modal amplitude. So we have the problem solved. The only problem will be that we'll have to do this for every different liner and every flow velocity. So the preparation will be a bit more complex, but we know how to compute the commands that will favor one desired mode. And here are the results. So if I want to, with this technique, to help the plane wave more than the other modes, here are the results in terms of modal amplitude for the plane waves in the left top corner. And you see that now I'm reaching nearly 20 dB of emergence before 2500 Hertz. And after, we have still an emergence between 5 and 10 dB. And actually it's working better with higher order modes, with a global emergence greater than 10 dB at every frequency. So this is very promising, but this has to be extended in the case of flow. Just a reminder now, a comparison between beamforming and pseudo-inversion. So it's not very impressive for the plane wave, but for the higher order mode, as the second higher order mode, we see that the emergence is much better with the new method. So still no liner and Mach 0. I will conclude with this slide, where I can compute some transmission loss measurements for a single degree of freedom liner with outflow on the top row and with Mach 0.2 on the bottom row, and with different incident acoustic field, so different modes. But I compute the overall transmission loss in dB, so calculated from the transmission coefficient between each mode. And we want to do that because we think it will lead us to a very interesting way of characterizing a liner in the environment of the duct, which is already the case because you see that in a precise installation, as it is the case with our duct, the liner is affecting very differently the several modes. So this, of course, has to be extended to representative condition, to mostly by that I mean Mach 0.6. We want also to send not just one mode, but a combination of modes that could be characteristic of the aircraft application, or also of what our colleagues in numerics are doing with, for example, equipartition of energy. So plenty of things to do, but I was happy to present you these promising results of modal control and decomposition in the duct with flow. And the perspective are firstly works at Mach 0.6. So you can see a characterization of the flow we have done at the place of the test section, so without liner, still our duct, with lots of pitot measurements. So there is some kind of an interpolation also to present you this map. But actually, yes, it's how will be the flow at this speed in our duct. Thank you. Have a nice day.